Welcome to this lecture on crystal structure, fundamentals and applications. This session is designed as a comprehensive guide for undergraduate students in materials science and engineering. We will be moving through a 20-slide presentation that covers the essential concepts of crystalline materials, from their basic building blocks to the mathematical ways we define their internal geometry. Let's begin. First, let's define our subject. A crystal structure is a unique arrangement of atoms, ions, or molecules in a solid material. It is defined by a regular, repeating pattern that extends in 3 dimensions. Refer to the 3D crystal lattice structure visualization. The key characteristics to remember are long-range order and symmetry. Because these repeating unit cells form the entire structure, they are the primary factor in determining a material's physical and chemical properties. To speak the language of crystallography, we need a few definitions. The unit cell is the smallest repeating unit that shows the full symmetry of the crystal structure. We identify lattice points as the specific locations in space where atoms or molecules sit. To describe a unit cell's geometry, we use lattice parameters. These include the edge lengths, labeled as A, B, and C, and the interaxial angles, known as alpha, beta, and gamma. Refer to the 3D unit cell diagram showing A, B, C, alpha, beta, and gamma. Finally, while there are many crystal systems, there are exactly 14 distinct three-dimensional lattice types that can fill space without any gaps, known as Bravais lattices. Every crystal belongs to one of 7 systems. In the cubic system, all sides are equal and all angles are 90 degrees. Tetragonal structures have 2 equal sides, A and B, but a different length for C, while all angles remain 90 degrees. In orthorhombic systems, none of the sides are equal, but all angles are still 90 degrees. Moving on, the hexagonal system features 2 equal sides with angles of 90 and 120 degrees. Rhombohedral has all sides equal and all angles equal, but those angles are not 90 degrees. Monoclinic has no equal sides and only 2 90-degree angles. Finally, triclinic is the least symmetric, with no equal sides and no 90-degree angles. The cubic system is the most symmetric and is very common in engineering metals. It consists of 3 types. The simple cubic lattice has 1 atom per cell and a packing factor of 0.52. The body-centered cubic, or BCC, has 2 atoms per cell and a packing factor of 0.68. This is found in metals like iron. The face-centered cubic, or FCC, is the most efficient, with 4 atoms per cell and a packing factor of 0.74. Copper and aluminum are classic examples of FCC structures. Image comparing simple cubic, body-centered cubic, BCC, and face-centered cubic, FCC, unit cells. In the tetragonal system, the unit cell is shaped like a rectangular box with a square base. Here, A equals B, but does not equal C, and all angles are 90 degrees. Titanium dioxide is a common example. The orthorhombic system has a unit cell where no sides are equal, A does not equal B, and B does not equal C, though all angles remain 90 degrees. This system is very versatile and includes 4 different Bravais lattice types: simple, base-centered, body-centered, and face-centered. The hexagonal system is characterized by a top and bottom that are hexagons. This structure is very common in metals like magnesium and zinc. Refer to the hexagonal close-pack diagram. Notice the specific HCP arrangement. The rhombohedral system, also called trigonal, is like a cube that has been stretched along its diagonal. All sides are equal, and all angles are equal, but they are not 90 degrees. This is the structure you will find in quartz and calcite. As we reach the lower symmetry systems, we find the monoclinic system. Here, no sides are equal, and it has 2 90-degree angles and 1 oblique angle. This is the structure found in gypsum. Lastly, the triclinic system has the lowest symmetry possible. No sides are equal, and no angles are 90 degrees. It is the most complex to describe mathematically and is found in minerals like turquoise. To label specific planes in a crystal, we use Miller indices, written as H, K, L in parentheses. To find them, follow these 4 steps. First, determine the intercepts of the plane on the 3 axes. Second, take the reciprocals of those intercepts. Third, clear any fractions to get the smallest whole integers. Finally, enclose them in parentheses. Remember that parallel planes always have the same indices, and a 0 index means the plane never touches that specific axis. To wrap up, let's distinguish between planes and directions. While planes use parentheses, crystallographic directions are vectors and are written as U, V, west in square brackets. Refer to the significance section. These orientations are not just academic, they are the reason why materials have specific mechanical properties. They determine the slip systems that allow metals to bend and the pathways that atoms use to move through a solid. Understanding these coordinates is the key to engineering better materials. While we have discussed the perfect crystal lattice, real materials are never perfect. Crystal defects are irregularities in the repetitive atomic arrangement. These are not necessarily bad, in fact, defects are often intentionally introduced to manipulate a material's properties, such as increasing the strength of a metal. We categorize these defects by their dimension: point defects, line defects, and planar defects. The simplest defects are point defects. A vacancy occurs when an atom is missing from its normal lattice site. In contrast, a self-interstitial occurs when an extra atom is squeezed into a small void space between regular lattice sites. Because atoms are larger than these void spaces, interstitials cause significant local distortion in the surrounding lattice. Line defects, known as dislocations, are one-dimensional defects around which atoms are misaligned. There are 2 primary types: edge dislocations and screw dislocations. Dislocations are the key to understanding ductility. When you bend a piece of metal, you are actually moving millions of these dislocations through the crystal structure. The path they follow is determined by the slip systems we discussed earlier. Planar defects are 2-dimensional boundaries that separate regions of the crystal. The most common example is a grain boundary, where 2 small crystals, or grains, with different orientations meet. Materials with many small grains are often stronger because these boundaries act as roadblocks for dislocation movement. Volume defects, like pores or cracks, are even larger 3-dimensional irregularities. How do we actually see these structures? We use a technique called X-ray diffraction, or XRD. Because the distance between atoms in a crystal is similar to the wavelength of X-rays, the crystal acts as a diffraction grating. When X-rays hit the crystal, they scatter in specific directions, creating a pattern that we can measure to determine the exact arrangement of the atoms. The fundamental equation for X-ray diffraction is Bragg's law. It is written as n times lambda equals 2 times d times the sine of theta. In this equation, lambda is the wavelength of the X-ray, d is the spacing between the crystal planes, and theta is the angle of the incoming beam. When this condition is met, constructive interference occurs, producing a peak in our data that tells us the distance between atomic planes. An XRD pattern consists of several intensity peaks plotted against the diffraction angle, 2 theta. Each peak corresponds to a specific set of Miller indices, like the 110 or the 111 planes we studied earlier. By analyzing the positions and heights of these peaks, materials scientists can identify unknown substances and determine if a metal has been stressed or heat-treated. Let's apply this to a real-world example: iron. At room temperature, iron has a body-centered cubic structure, known as ferrite. However, when heated above 912 degrees Celsius, it transforms into a face-centered cubic structure called austenite. This atomic shapeshifting is exactly why we can harden steel through heat treatment. We are changing the crystal structure to trap carbon atoms. It is important to remember that not all solids are crystalline. While crystals have long-range order, amorphous solids like common glass have only short-range order. Amorphous materials lack the distinct melting points and predictable cleavage planes found in crystals. This difference in atomic packaging results in vastly different transparency and brittle fracture behaviors. To conclude, we have explored the foundational geometry of the solid state, from the 7 crystal systems to the identification of planes and directions. We have seen how imperfections and orientations determine the strength and utility of materials. As you continue your studies in materials science, remember that everything, from the silicon chips in your phone to the aluminum in an aircraft wing, starts with the crystal structure. Thank you for your attention.